population 3 stars or collapsing clusters or other favorite model. There may or may not really need to be a strict requirement on zero metallicity gas, but that is something that we do put in these simulations to mimic some of those predictions. Yeah?
Sorry, I think I missed something earlier. So you're not just putting in the black holes by hand and then following them. They're actually being formed self-consistently in the simulations.
Indeed.
Okay, cool.
Yes, yes. So low metallicity gas with a temperature range and a low molecular hydrogen fraction is also required. For particles with a high molecular hydrogen fraction would be predisposed to form stars instead of forming black holes. All right. The next figure is the mass of the halo at the time the black hole forms. So this is another histogram. Each shade of purple represents a different simulation, but the total histogram is all of them put together. And from this we can see that the halo mass of black hole, or of the host halo at the time the black hole forms is pretty small, 10 to the 8 to 10 to the 9 solar masses or so, with a bit of a range here. But these are very small halos, so this is halo mass, this isn't stellar mass. And so we find that it's very, very important to be able to form black holes in these small halos, because that's where they seem to be forming. That's where predictions for direct collapse and for population 3 stars suggest that they will form. And if one wants to have dwarf galaxies with massive black holes in them, those are small galaxies as well, you need to be able to form a black hole in a small galaxy. You had a question?
Yeah, so does every halo have a black hole, or are there halos without a black hole?
There are definitely halos without black holes. I think my next figure is the occupation fraction. So I'll show you how the fraction of halos with black holes varies over time.
What are the masses of the black holes?
The black holes form with a mass of 50,000 solar masses. Yeah. Yeah, so not every halo has particles that meet the criteria for black hole formation. So what I have here is the occupation fraction of halos with black holes at redshift 0. Here I have it versus halo mass, and here I have it versus stellar mass, with magnitudes at the top for anyone who speaks magnitudes, which is probably not too many people in this room. So you can see that for very small halos at redshift 0, it's not very likely that they'll host a black hole, but as the mass increases, it's more likely. And then once you get up to more Milky Way size masses off the plot here, then all of the galaxies will host a black hole. And so it's definitely very mass dependent as well as dependent on the stellar mass.
So you're saying that definitely ultra faints don't have black holes?
I'm not saying that definitely ultra faints don't have black holes. I'm saying that this sample size is not, actually I think we do have an ultra faint with a black hole, but I'm not. Let's look at the next slide. We'll show
Maybe
that.
it's because the lowest mass is 50,000 solar masses, so there is not enough variance there.
Yes. So this sample is definitely not a large statistical sample of galaxies. So I wouldn't say ultra faints don't have black holes, and it's also dependent on the seed formation model. I'm saying it's possible that ultra faints could have black holes, but I wouldn't expect most of them to have one. But I think some could. There's a slight difference here in like the shapes of these occupation fractions, and that actually turns out to be an environmental effect, in that the dwarf galaxies that are near Milky Way galaxies have been tidally stripped a bit, and so they've lost some of their dark matter. So they have higher stellar mass to total mass ratios compared to field dwarfs. And so as a result, there's a higher fraction of galaxies in the largest stellar mass bin that has black holes compared to the halo mass bin, but that's just because dark matter has been lost in some of these galaxies, and so that shifts them this way in this plot, but not in this plot. Yeah?
Sorry to keep asking questions, but
That's all right.
does this, do you self-consistently account for black hole mergers and resulting kicks? So does this at all reflect black holes being kicked out of halos, or not?
This does not reflect black holes being kicked out of halos by mergers and gravitational recoil.
It's purely as a result of
Yes,
formation.
yes. Now that's something that I want to begin to focus on now that we have high enough resolution and a dynamical friction model, that I think now that's a step that we could take, but at this time we have not taken that step. So these occupation fractions would be upper limits, because some of these may have been kicked out of their halos after black hole mergers. I will talk about mergers towards the end of the talk, so we will revisit this. All right, so something that I wanted to check is to see if the host galaxies of massive black holes, the dwarfs, can be differentiated from those that don't host black holes. Because these black holes are hard to detect. A lot of them are not accreting now, if they were ever accreting. And so I wanted to see, is there some sort of characteristic way that we can determine if there is a black hole in a galaxy? So this figure shows the stellar mass-halo mass relation of all of the galaxies in the entire simulation are gray. The ones that have black holes are stars, and the ones that are, let's see, the open stars are the ones in the Justice League with the Milky Ways, and the solid stars are the ones with the that are in the MARVEL-ous dwarfs that are isolated. And what I was hoping is that there would be some overall difference between the black star points and the gray circle points, saying that maybe black holes will cause some sort of different stellar properties compared to ones without, but they are all within the scatter.
But
Yeah.
I must be missing something. You said 50,000 solar masses for the black hole.
Yes.
The mass in stars is not very different from the low mass ones. So
Right.
then the black hole should dynamically be quite significant relative to the stars.
In this one,
Well,
yeah.
when the stellar mass is about 100,000
Mhm.
solar masses, the black hole
Right.
mass is comparable to the stellar mass.
It's true.
So
Yes.
you should see some dynamical effect.
We could possibly see a dynamical effect. I don't know if we resolve that dynamical effect in the simulations. But on this figure, there's no way to differentiate at this.
Though the
Right.
halo mass is much larger, so maybe the stars aren't contributing much to the kinematics.
That's the question in the core, yeah.
Yeah.
But one would expect if you have a dark object of the same mass as the stars that you would see something.
One would expect that. Yeah, I don't know if we can resolve quite that much of a dynamical effect. Another way that I tried to look at this was star formation histories. So what this one is showing is cumulative star formation histories. So redshift infinity to redshift 0, how many stars have been formed over time. The dwarfs hosting black holes are all the dark lines, and the gray lines are local group dwarfs from Dan Wise's sample of doing resolved star formation histories using stellar population studies. And basically, all you can see here is a big mess of lines, which shows that there's a lot of variety in both the simulated star formation histories and the observed star formation histories, but there's no obvious difference between the two samples. So in terms of stellar populations, it's not, at least from the simulations that I have in hand, it's not obvious that there's a way to tell just by looking at the stars if there's a black hole in a galaxy versus whether there isn't. Yeah?
So is this happening because basically, I don't know, supernovae and stuff are essentially just killing off all the gas before the black hole can actually do anything useful?
I will tell you why it happens now. So why does this happen? Here are some pictures of some of the dwarf galaxies. These are all from the Sandra simulation. These are the ones that are hosting black holes. And so I'm showing each of them face on and edge on, face on and edge on. And there's a cross that represents where the black hole is. You may notice that some of the black holes are off-center. This one is nicely in the center. This one is a little off. This one is totally off. Some of them are off-center. Remember that we have a prescription for dynamical friction. And so, to the best of our abilities, we believe that if a black hole should be in the center, it will be in the center. So why are these not in the center? Good question. It turns out that if you look at the distribution of all of the black holes in all of the simulations, here's a histogram of the distance from the center. There's a big peak here. About half of them are in the center, and about half of them are off-center. So about 50% of black holes in dwarf galaxies are off-center, which will make them extra hard to find. So why is this? Here's an example of some work that my community college students did over the summer of the distance from the center of their galaxy versus time of 3 black holes in one simulation. You can see that this blue one stays in the center the whole time. The green one starts in the center, it gets kicked out, sort of comes back, but then leaves again. And then this yellow one, something funny happens here, but then it's mostly in the center, and then it disappears as well. So what's going on with that? It turns out that dwarf galaxy mergers are the things that are causing this. So I can show you a little bit of a, I don't know, it's not a movie. Here is a tiny, tiny galaxy at redshift 4.8. It has a black hole in it, which I've stuck in PowerPoint because you can't see it otherwise. And I'm going to show you, flip through some redshifts, 3.8, 3.1, 3. Here's somebody coming. There's a little gray spot there. Here is the friend that comes by. It's a larger galaxy. These galaxies sort of circle each other for a little while. And eventually, this tiny one that the black hole was in gets swallowed up by this larger galaxy. And this black hole, once it's in this larger galaxy, does not actually find its way to the center. It stays wandering in the outskirts. Because in the outskirts, there's not a lot of matter there. Dynamical friction timescales are long. It does not work its way into the center. And that seems to be the case for all of the galaxies that have off-center black holes. It's that they form in the center. There's a merger, usually with another dwarf, that perturbs the galaxy and makes a big mess. And as a result, the black hole ends up wandering in the outskirts. In some cases, there's more than one black hole in a dwarf galaxy. So in this case, there's a central one with a mass of about 1 million solar masses, and there's one on the outside with 50,000 solar mass.